we should move on to our next speaker, Professor Daya Shankar Kulshreshtha, who's who's a senior colleague of mine. I'm happy to welcome him for his talk on boson stars.
Thank you, Sanjay. Thank you very much for your very kind words. And then let me first extend my heartfelt thanks to my friend Alok Mitra and his tech team for doing a very, very wonderful job on this for this meeting. Today is the birthday of my Guruji, Professor A.N. Mitra. I would say only half a line that Professor Mitra was very, very fond of me. And he would love to have a cup of tea or coffee with me, depending upon if he were in the department. At home, he would usually make the coffee himself, insist on making it himself. So with that, let me share my screen. Sanjay, could I share my screen?
Absolutely, absolutely. The floor is yours.
Okay. So all right. So with those words, let me then start on the topic of my talk. And one of my collaborators, my kind of guide and mentor in this particular field is Professor Yuta Kun, who happens to be here already. My other collaborators are Sanjeev Kumar, Usha Kulshreshtha, of course, Yuta Kun, Sarah Kallen from Oldenburg, and Sushil Arora. And this talk is based on a series of publications beginning with 2014. So classical and quantum gravity, general relativity and gravitation, physical review D, rapid communication, physical review D, regular physics letters B, few body systems, European Physical Journal C, and this wait a minute. Oh, something went wrong. Let me just have a I'm sorry for the interruption. And maybe I made some mistake.
We can see your slides. We can see your slides. Perhaps the next slide is
I'm not able to see my slides myself. Can you help it? In this talk, I'm going to present a few field theoretical models of boson stars and the field theoretical models of complex scalar fields coupled with gravity provide the non-singular asymptotically flat solutions which are referred to as the boson stars, which are the gravitational bound states of scalar particles. In general relativity, a non-singular asymptotically flat solution refers to a solution that describes a space-time which is free from all singularities, that is, no points of infinite curvature at any point, while still exhibiting the property of being asymptotically free. So it means that geometry approaches the flat space-time of special relativity at very large distances. At very large distances from the source of gravity. Boson stars are hypothetical astronomical objects that consist of particles called bosons. Scalar fields occur routinely in particle physics, field theory, gravity theory, string theory, and cosmology. And scalar fields interacting with gravity through a gravitational condensation mechanism might form spherically symmetric objects, the boson stars, that would be stopped from collapsing by Heisenberg uncertainty principle. The boson stars were conceived almost half a century ago, and they are very interesting from theoretical point of view. Their potential astrophysical applications are of wide interest. Accretion disks around boson stars have been studied. Gravitational wave signatures of boson stars have been studied. Binary systems of boson stars have been studied. Discovery of hairy black holes based on boson stars have been studied. And it has also been discovered that rotating boson stars allow for static orbits. So Olden Group, led by none other than Professor Yuta Kunj, has been at the forefront of many of these studies. And just like supermassive black holes, boson stars could exist even at the center of galaxies and could possibly explain many of the observed properties of active galactic core. Boson stars could have been formed, for example, through gravitational collapse during the primordial stages of the Big Bang. It may be possible to detect them by the gravitational radiation emitted by a pair of co-orbiting boson stars. Gravitational lensing by boson stars has also been studied, and they have also been proposed as the dark matter candidates. They have also found applications based on the ADS-CFT conjecture. Amongst the important properties of boson stars, their mass, their size, and their particle number, which is proportional to their charge, are of great interest. Particle number of boson stars arises from the U1 symmetry of the underlying theory, which gives rise to the conserved current and the associated charge. Also, when U1 symmetry is made a local symmetry, charged boson stars arise. So I will be presenting three models. Two of them will have local gauge symmetry, and the other last one would have a U1 phase symmetry. So they will not be charged, but the first two ones would be the charged boson stars. So boson star solutions could in principle be obtained by employing any self-interaction scalar field potential. And these theories are interesting because they are perfectly well behaved from physical point of view, and they lead to compactness of solutions. Here, compact is meant to describe a solution whose scalar field vanishes identically outside a compact region of space. Oldenburg group in particular has made extensive studies of boson star solutions and concluded that the impact compact boson stars arise when a V-shaped conical self-interaction potential is employed. The boson stars in a theory without a conical potential do not feature sharp boundaries. In compact boson stars, scalar field is completely confined to a finite region of space. Now, also, boson star solutions do not exist for arbitrary values of the parameters. They exist only for a certain domain of the parameters. In our work, we first obtain the domain of existence of the parameters of the theory for which boson star solutions exist, and then study the various properties of the boson star solutions. Now, let me come to the first model, which is described by this action. So you have the Ricci scalar R and the cosmological constant lambda and the matter field Lagrangian, and this is the minimal coupling term. So U1 gauge field, kinetic energy, and the complex scalar field. And this is the potential. So this is a model of massive scalar fields, and this is a conical potential. Now, in this conventions, when lambda is positive, then it's a de Sitter space, and when lambda is negative, it's anti-de Sitter space. So the usual procedure, variational principle, gives rise to the equations of motion. The first one is the Einstein equation, Maxwell's equation, and then the Klein-Gordon equations and its complex conjugate. Of course, they are coupled nonlinear differential equations, and this last one is just the energy momentum tensor. So we assume that A and N, the metric functions that appear in the definition of the line element or the metric tensor, are functions of R only, not of T, theta, and phi. And so for spherically symmetric solutions, we adopt a static spherically symmetric metric with Saussure-like coordinates given by this. Now then, making use of the conventional definitions of the Christoffel symbol, Ricci tensor, and Ricci scalar, etc. As you will see, all of them, they depend only, they can be derived from this J mu nu. And so eventually here they are functions of A and N and their derivatives. So the Einstein equation, this is the Einstein tensor, and this is the Einstein equation, in the component form can be written like this: T, R, theta, theta, phi, phi. The last two equations yield identical results. An important ansatz that we make for the matter fields is phi expressed in terms of this, and A mu dx mu is ATR dt. So we work under the assumption of vanishing electromagnetic field, which implies divergence of A equals to 0. This leaves us only with time-like component of A mu. Space-like components of A mu do not contribute in this assumption. Now, you see, in this theory, we have some constant parameters which are dimensionful, and the field variables H and B are also dimensionful. A and N are dimensionless. So we construct new variables. So we define new constant parameters in terms of the old ones. So the new ones are dimensionless. And the field variables are also defined, reconstructed so that this H and B are dimensionless. Then we also like to make the argument of the fields to be dimensionless. So we define R hat equal to MR. And with this, these are the new definitions of the scalar matter field and the vector matter field with dimensionless arguments. So this eventually the equations of motion, they reduce into this set of 4 equations. This is scalar matter field for the U1 gauge field and for the metric function. So these are, they are obtained from the Einstein equations. Then you choose the appropriate set of boundary conditions and for the boson stars and for the boson shells. So here, of course, the outer region, the boson stars, we match the exterior region outside the boson stars with RNDS or ADS solutions. And in the boson shells, we match the interior region R less than Ri and the exterior region R greater than R0 with the appropriate RNDS or ADS solutions. So the U1 invariance of the theory would lead to the conserved Noether current and the corresponding charge density and the global charge Q. And the mass parameter M of the theory is given like that. So then I'm going to present some phase diagrams. And this phase, here I like to explain that in our studies of the phase diagrams of boson stars, we find that a passage from one set of phase trajectories to another occurs suddenly or catastrophically. In the bifurcation phenomenon, when a sudden change in the behavior of the phase trajectories occurs as a parameter passes through a critical value, then the phase point corresponding to that critical value of the parameter is called a bifurcation point. In our model that we consider, we obtain up to 4 bifurcation points. However, in the entire series of papers, we eventually establish that an infinite sequence of bifurcation points exists in the phase diagram of the boson stars. Also, if a system contains more than one parameter, then each parameter has its own bifurcation points. Now, let me show some results. So this is very important result. This is a scalar field at the center of the star. This is the vector field at the center of the star. And let me recap that when we started working or picking up this field from my collaborator, Professor Yuta Kunj at the University of Oldenburg, she already had, this was around 2010, she and her group, they had discovered this particular bifurcation point when we started working on this project. And you see here, these are the, in the region 1A and 1B, there are some phase trajectories. And when the parameter lambda, the cosmological constant, passes through this particular value, then they immediately change from, they now appear in the region 2A and 2B. So there is a sudden change, you see, from 1A, 1B, now they disappear in those A domains and they appear here. So around 2010, when Sanjeev passed out his master's degree, he was keen on working with us. And we had picked up some of the basics of this work from Utah at Oldenburg. So I suggested to Sanjeev that if it interested him, he should work on this. And he liked the idea very much. And then he worked for some time to develop his own computer program, which today is a rather $1 million computer code or computer program where his numerical accuracy is very, very accurate, up to several digits. So you see here, this portion is being blown up here to show more bifurcation points, 3, 4, and so on. 1 and 2 are visible here. This is another set of phase space variables, A0, metric function and the vector field. So then this is A0 versus H0. In each diagram, you notice some of these asterisks appearing on these figures. They actually correspond to the transition from a boson star to a boson cell in each one of them. In each one of them, these asterisks, they signify, here you find some. So now we, after this these successful results, we thought of making three-dimensional plots. And here I would like to define the viewing angle. If you see, I look at the room from one corner, another corner, third place, fourth place, the room would look different. So one has to define the viewing angles, theta, phi. So theta denotes the angle of rotation about the OX axis in the anti-clockwise direction, and it can take values between 0 and pi. Phi is the angle of rotation along the OZ prime axis, which is the new axis obtained after rotation, first rotation. And it can take values between 0 to 2 pi. So now, so this is a three-dimensional plot of metric function A at the center of the star, vector field at the center of the star, a scalar field at the center of. And but the viewing angle here is 60-170. Now I will show you a few more that they each one corresponds to a different viewing angle, 60, 240, and so on. So the same three phase space variables, but a few figures showing the view with different viewing angles. Now we drop A0 and we make plot of B0, H0, and the radius of the boson star, and again obtain those three-dimensional phase diagrams of the theory. Some of them are more clearly visible than others, and so just the viewing angles change. This is just the distribution of the field. So we know that the matter field H is for the boson star would lie within a certain domain. So boson star from 0 up to the radius of the star. And the other three fields are either electromagnetic field or gravitational fields. They are long-range forces, so they continue. In this, the inner radius of the boson cell, it has just started the formation of boson cell. In this, the boson cell, these correspond purely to boson cells. Ri is greater than 0. And of course, when lambda is positive, they correspond to the de Sitter space. And when lambda is negative, so the next two figures I show for the anti-de Sitter space with the same distribution of fields. Now, after that, I go to the next model. This is this corresponds to a, here the scalar field is massless. So only conical potential is there, and there is also no cosmological term here. So you now, but the scalings here, now parameters are different. So the rescaling definitions would be different. We again follow the same procedure. We construct dimensionless constant parameters and dimensionless fields, then also make the arguments of the fields to be dimensionless. And then we study, so we end up with these four equations of motion, which are converted from covariant form to this component form. And again, the U1 invariance of the theory would lead to the Noether conserved Noether current and current density, so charge density and the global charge and the mass parameter M. So in these two models, this is local symmetry. And now we, after doing some of these things, we found that our first four bifurcation points were very, very impressive. They seem to be correct up to 8 digits. So we made this conjecture. If there is a regularity in the occurrence of the bifurcation points, we found it tempting to discover, could there be a whole sequence of bifurcation points, maybe waiting to be discovered, which might display a self-similarity. So we made this conjecture. So here this A, F, and B are constants. And then, so we used the first three bifurcation points and made a prediction for the fourth. And Sanjeev's program gives the fourth one exactly located at this point. So going up to fourth bifurcation point already is very, very challenging, because one has to go up to eighth digit of numerical accuracy. But this conjecture seems to work perfectly well. It seems to be tested here. Now here, these are the phase diagrams of this second theory, second model. Here there is no cosmological constant. However, there is this constant parameter A. So we study this set of bifurcation points with respect to the variation of A. So you can clearly see the first bifurcation point, second bifurcation point, third bifurcation point, and so on. And this part of the diagram is blown up here, zoomed here. So you can see B3. And here it's further, this particular little domain is further zoomed to give you the fourth bifurcation point here. So it's very fascinating and very interesting. In fact, American Physical Society praised our work in their two different articles, where they praised our work on this bifurcation points. Then this is a two-dimensional plot of A0 versus B0. This is A0 versus H0. Then these are three-dimensional plots. The logic is as before. The viewing angle is 60 and 100 between A0, H0, and B0. So with different viewing angles, we see a few of these plots. Let me go slowly. So, and then, then we change the A0 by the R0. If it were possible, one could practically, if it were practically possible, one could, because we have a whole set of this value of R0, A0, H0, V0, and so on. One could plot all of them, but we go only up to 3 dimensions. So here it's the radius of the boson star and matter fields at the center of the boson stars. So then with this different viewing angles, you find this. After that, I would come to the, no, is this, yes. So I then finally come to the third model. I have so far presented 2 models, one with massless scalar field without cosmological constant, and the first one was massive scalar field in the presence of cosmological constant. Now here we try a different thing. So this is just a new series of our papers in this direction. And in fact, this is the first paper with non-minimal coupling. So this gives you square root of minus g d4x, gives you the minimal coupling. However, if you include some such term where there is a direct product of the Ricci scalar with phi star and phi. So this parameter chi couples this R and phi star phi. This corresponds to non-minimal coupling. This paper has actually just appeared last month in Classical and Quantum Gravity. So variational principle gives you these 3 equations of motion, and you again construct dimensionless constant parameter, which is only one alpha, and dimensionless field variable h. There is no vector field here. There is no U1 gauge field here. So only h and alpha. Then you again make the argument of this field to be dimensionless, which is r hat. So this is the dimensionless field variable with dimensionless arguments. So actually, these are the equations of motion that you eventually obtain through the variational principle and writing them down. So this is these are for the metric functions, and this is for the scalar field, matter field equation. And these are, so this you obtain from the Einstein equations, these 2, and the last one. So you see here that equations are little more involved because of the presence of the non-minimal coupling term in the theory. So that is the point. You again choose the appropriate boundary conditions. Here, the U1 symmetry of the theory would be a U1 phase symmetry. So because it's a global symmetry and not a local symmetry, as it happened in the first 2 cases. So you again obtain the charge, global charge of the boson star and the mass parameter m of the boson star. With that, then I just present a few results. So in this figure, we plot matter field at the center of the boson star versus the parameter alpha, and this for different values of chi, which couples, which gives you the corresponds to the non-minimal coupling term. So you see, when you increase chi, what happens? This term, this plot comes down here. This black one corresponds to xi equal to 1, this one. And this corresponds to xi equal to, so non-minimal gravity. And this is minimally coupled gravity. So as alpha increases, it H0 initially decreases like this, and after some limiting value of alpha, it starts monotonically rising and finally ending up into the damping. So,
Professor Kulshreshtha, you have 3 minutes.
okay, thank you, Sanjay, thank you. So the second one is the plot of the radius of the boson star with alpha for different values of xi. And here you see initially when we increase alpha, the radius of the boson star decreases, and after this value, it again starts increasing and then eventually ending up showing you the oscillating pattern, which actually corresponds to the oscillating pattern of the matter field at the center of the star. So this is the spiraling pattern of the radius R0, which is blown up here in this figure. And if you plot mass versus alpha for different values of xi, the results are so transparent that you see increasing xi implies that the coupling of a scalar field with gravity increases and increases. So this allows to sustain higher masses and enable the formation of more massive and more compact boson stars. So this is the thing which is very clearly visible here. And the charge parameter, the global charge of the boson star, also follows the same pattern as that of the mass. So a spiraling effect here after this value limiting alpha, and prior to that, it increases along with the increase in alpha. So this is mass with respect to radius. So when you reduce the radius, the mass increases. You see, when you reduce the radius this way, the mass increases, or other way around. So, and the same applies also the charge of the boson star. This is the last figure, which shows the mass versus the charge. Yuta very much loves these figures. And here you see that M increases linearly, almost linearly, up to this limiting value of alpha. And then it starts making, it's not so visible here, but then you get these spirals here. So after this alpha, this value alpha going to alpha max, a spiraling behavior is observed, and this is becomes more massive as we increase xi for a fixed value of alpha. So with this, I think I'm through with the all my results. At the end, I would just present the a quote from Mr. Pythagoras, who said, "Stars in the heavens sing a music if we only had ears to hear." With that, I would end my talk. And thank you once again, Sanjay. Thank you, Alok, very much.
Thank you, Professor Kulshreshtha. The talk is open for questions. We can have one brief question in view of the time.
Okay, welcome.
I see Professor Haridas.
Yes.
Your hand. Okay, that is not a raised hand. Is it a raised hand or is it a clapping hand? Okay, that's a clapping hand, not a raised hand. Okay, so I'm just looking for raised hands, and at this point, I do not see one. So, Professor Kulshreshtha, thank you very much. For this talk. Gargi, did you want to say something? Gargi, you're muted.
Okay. Okay. So,
okay, fine. So I think that in view of the time, we will proceed further with